Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on PVTP software about compositional oil modeling. Right, in previous sections, we have completed the PVT report and the PVT sample. If we enter this PVT sample, we have populated this section with the components. And remember, we have one pseudo component here. Pseudo component here includes C7 plus components, and we also know the composition, and we also have laboratory data that we have imported into the PVTP. Okay, we have saturation pressure data, constant composition expansion, separator, and differential liberation. Okay, so now we will continue forward by defining the pseudo component. Here we have add pseudo properties. We will work on this tree in the upcoming videos, including this video. Okay, so first, highlight this, the PVT sample, and then double click on this, add pseudo properties. Okay, so now you can see we have two more blocks, new blocks. The first one is pseudo properties and the PVT fluid. We have two new items inside our characterization wizard. By the way, on the left side, we have characterization wizard. On the right side, later on, we will use this side. We have calculation wizard. Okay. All right, so it's pretty interesting. Now we will work on our job inside this pseudo properties. So double click on the pseudo properties object. All right, now we need to deal with pseudo properties, volume shift, splits pseudo, later on we will use that, and binary interaction, input data, and lastly the output fluid. All right, but in this video, we just want to talk about pseudo properties. So let's review the window. Here we have collapsed heavy components to how many pseudo components you want. We will start with one. And then boiling temperature. Okay, we will determine the boiling temperature using three available correlations, either petroleum experts, standing and cuts, and other correlation. And then we have critical properties like critical temperature, pressure, volume, and omega. By default, we will use this TWU admixture, but you can exercise with, other correlations available here. Okay, and then the molecular weight, specific gravity, boiling point, temperature, mode, we can compute either boiling temperature or molecular weight or specific gravity or none, depending on the unknown that you have. And critical properties mode, either automatic and manual. And here we have include the pseudoname automatically populated by the PVTP using the data inside the PVTP sample. Okay, and then we know the mole percent. Let's see if we can double click. Okay, we can open them both. So here we have the composition 32.1 and the molecular weight also automatically transferred from PVTP sample to this pseudo property. So now the data that we have is the mole percent, we know the name, of course, and the molecular weight. Okay, I'm going to click on OK here. All right, so once again, in this window that opens, the pseudo components critical properties are estimated from correlations, the correlations that we have, using an input of pseudo molecular weight or specific gravity, SG, or boiling point temperature, depending on what data that you have. Okay, these critical properties are required such that the equation of state can perform any calculations. Okay, and here, once again, we have the molecular weight entered from the PVTP sample transferred to this. Okay, this object has already been carried over so that only either specific gravity or boiling point temperature, BPT, that are required for the critical properties to be estimated. Okay, if one of the three inputs is not reported in lab data, then we can estimate the value from correlation. In our case, all right, we already know the molecular weight, and unfortunately, the boiling point temperature is not reported, and we need to estimate from the provided molecular weight and specific gravity. Okay, and by the way, we also know the specific gravity for this pseudo component, and we will populate the data here. The value is 0.87. Okay, so if you have your lab report, you know the molecular weight of the C7 plus component. You also know the specific gravity. That's good. Now you can estimate the boiling point temperature. If you don't know the molecular weight, but you know boiling temperature as well as the specific gravity, then you can select this. Okay, then this will be blank and you need to input boiling temperature or specific gravity. Or if you know specific gravity, then you need to provide molecular weight or boiling point temperature. If none, then yeah, you just input all of them. But now we don't know the boiling temperature. So let's estimate using the correlation that we select as well as the molecular weight, then specific gravity that we know. Okay, but before pressing on this calculate button, let's see, we also have another feature, which is auto match of densities via boiling point temperatures. Okay, here, this option for auto match of densities via boiling point temperatures are selected by default. This is specifically developed by the software provider, by the petroleum experts. This means that when the object is calculated, the auto match process will be performed unless the user decides otherwise. So you can enable them or enable them. If you enable them, okay, so you can see this include. If you enable, this will be, this will erase this include column. Okay. All right. Let's see. We have enable auto match, use zero binary interaction coefficient check, and match oil viscosity check, and density method, either coastal or standing cuts. This is the maximum iteration, and this is the number of the iteration and the calculated error. All right, the standing cuts by default is used. This method for calculating liquid phase density is known to provide accurate results close to standard conditions. All right, so as part of the auto match, this PVTP performed two calculations of the liquid phase density in parallel. On one hand, the equation of state is used to calculate the K values for a flash to standard conditions, from which the individual phase composition and in turn the density will be calculated. So that's the first thing. So PVTP will perform two calculations simultaneously. The first one is equation of state used to calculate the K values for flash condition. That's the first thing. And the second thing, on the other hand, the fluid will be flashed to standard conditions using K values from the Hoffman plot, which are in turn used to determine the phase composition. With the composition of the liquid phase known, then the standing cuts correlation will be used to calculate the liquid phase density. All right, so these are pretty good evaluation, pretty good computation. And please note that the use of K values from the Hoffman plot, unlike the equation of state, This will ensure that mass balance will be met. However, their use is somewhat limited to only ambient conditions where the tie lines are straight. Okay, so that's, in my point of view, it's more thermodynamics or chemical engineering point of view. But if you're interested in fluid, of course, you can learn more about that. All right. So, all right. So again, when automate is used, PVTP regresses on the pseudo-critical properties to match the liquid density predicted by the equation of state to that predicted by standing cuts by adjusting the pseudo boiling temperature. Okay, so that's the game plan. We have, equation of state that will predict the liquid density, equation of state. But in another calculation, we also have standing cuts that will estimate the liquid density by adjusting the boiling temperature of the pseudo component, which actually is our main product, the boiling point temperature on this specific phase or stage of the calculation, right? We want to know the boiling point temperature. So liquid phase density from EOS and liquid phase density from standing cuts will be matched with minimum error. That's what we expect. All right. Changing the boiling point temperature changes the value of the characteristic function such that a different K value is determined from the Hoffman plot, which alters the phase composition and therefore the calculated phase density from standing cuts. All right. However, changing the boiling point also changes the calculated critical properties such that the different K values and therefore phase composition and liquid densities are calculated. This process will be repeated until either two methods converge or the maximum number of iterations here is exceeded. All right. Okay, so that's lengthy explanation, but if you want to learn more, you can start with reading the PVTP manual, and you can go back and read your PVT textbook, all right, or fluid modeling textbook, something like that, so that you can understand more. But for us engineers, practically speaking, we just want to get the boiling temperature and the error at minimum value. That's the thing, so that we can continue in this process to get our model for the fluid that will be used for reservoir simulation or for material balance computation later on. Okay, so that's it. That's just for the explanation. The main thing here is just either you want to extend the iteration, let's say to 500, and just click on calculate button. Okay, but wait a minute. The following calculation errors have been found. Okay, failed to auto-match composition. The unmatched value have been used instead. All right, so let's check it out. What happens here? You see the last error is quite high. PS1, 32.1, and then molecular weight 220. Oh, this one I input 0.87, where I should use comma here in the software. So with maximum iteration of 500, let's click on OK, very good. So if I expand this window, all right, so you can see the error is 4.32 e to the power of -5, which is practically speaking pretty small. All right, and so we know that the boiling point temperature, or we estimate that the boiling point temperature will be somewhere 547 degrees Fahrenheit. Also calculated boiling point temperature here. All right, and then critical temperature, critical pressure, eccentric factor, critical volume. Very, very, very good. All right, so that's the thing about this video. In this section, we just want to populate the data here, and we get this boiling point temperature. Okay, on the next video, we will continue this exercise by using calculation with separator. But I think we can call it a day. We have already talked quite a lengthy explanation. So thank you so much and see you again.